Today I'm going to compare two different storage methods for real-time data streaming platforms with a focus on read and write latency. My name is David Kjerrumgaard, and I'm the author of Apache Pulsar in Action, and I am also a committer on the Apache Pulsar project, and have spent the last decade focused on distributed open source data streaming platforms, including Kafka, NiFi, Flink, and Storm. I want to begin this talk with a brief historical review of how data streaming platforms came into existence and their place in the data landscape overall. So in the late 2000s, LinkedIn was starting to run into an issue with scaling its data replication framework. It simply had too much data that needed to be shared with too many systems. As you can see from this image, shared from the original engineering blog published by LinkedIn, every system that needed data from multiple different sources had to have a single integration point set up for it distinctly. Worse yet, whenever a new data source came online, it had to be fed into end-consuming systems downstream. Obviously, the solution wasn't scalable. This led them to build a system, Kafka, that had the following characteristics and capabilities. It was a write once, read many times system. It supported in-order processing of messages, specifically for things like logs, as you can see here, operational logs and operational metrics, and it had to be horizontally scalable. This allowed them to have a single unified log instead of having to integrate each individual data source from here shown at the top and have to integrate them with the ones shown at the bottom. Kafka instead allowed each of these independent systems to publish to this unified log and then have the downstream systems then consume from this log to get the information they need and consume it at different rates. So it became rather than a point-to-point system, it became a centralized location and storage for data. Now the key to Kafka is the concept of a log. And a log is simply a time-ordered, append-only sequence of data where inserts where the data can be anything. In Kafka, it's just an array of bytes, and that's really it. But if this sounds like the basic structure that a database is built upon, it is. Because as you can see, logs weren't really revolutionary, right? This is not the big breakthrough that made Kafka what it is. Logs have been around way before 2010. In fact, logs have been used in databases since as early as 1981. And nearly all databases rely on a log data structure internally to buffer all the pending changes before applying them to the database tables themselves. This is often referred to as a change log, a write-ahead log, or similar terminology, but they all serve the similar purpose in that it ensures the proper ordering of the changes and represents the authoritative truth of what happened. And so since the log, when data is published to a database, it's actually persistent to this write-ahead log, and then it can be used to restore data, to replicate data, and basically track all the changes to the database itself. Within a database, this change log has a single consumer that processes the events sequentially, so there's no competing reading of the data. It continuously processes this data. It reads the event, updates the table or tables as necessary to make the changes, and then commits those changes within a transactional boundary using ACID semantics. And then once the data has been persisted, it deletes the event. That's it. So this pipeline is meant to be very efficient, and having a single consumer guarantees the correctness, in-order processing, everything that Kafka strive for, but you did it at a less horizontally scalable method. So really, this is nothing new, processing of the data and then using it as a replication method for changes into your system. Now the logs inside a data streaming platform are quite different. First off, they're designed to have multiple consumers rather than a single consumer. Each of these consumers can process the events at a different pace or even be offline for long periods of time before coming on and processing themselves, as shown here. So you can see destination system B is much further ahead in its processing than destination system A, which is further behind in the lagging consumer of the same events. To account for this, the logs in the data streaming platform are designed to retain the data for longer periods of time than a database change log is. And this data can be retained can be retained inside a streaming platform for days, weeks, or even longer. This fact led to the desire to build tools that could process these logs to perform analytics on these events, rather than waiting for them to get persisted into a database. Another insight that came to be once we had this data structure in place, this unified log, and this longer-term retention of data, was that you could actually query this data itself as it sits in its more natural state, and then you could provide some additional processing that wasn't able to before in a traditional database, right? So rather than querying the database, which represents the current state of the data after all events have been applied, these tools, these stream processing tools, allow you to perform queries over a subset of these events, time slices these events. So one common example is performing the same calculation over consecutive windows of data. For example, the average number of web page visits over a 5-minute period, started at 9 a.m. to 9:05, and then from 9:05 to 9:10, etc., and then comparing these values themselves. So as you can see, you can answer much more interesting questions around what was going on within your system, within your overall web page at a certain point in time. What is this SKU at this particular time? What was the average sensor reading over this period of time, and compare these tumbling window values to other windows, etc. These types of queries weren't possible before the advent of data streaming platforms. Again, databases weren't designed to have an event-based system. They were a single state-based storage of the data. They only would show the most recent information. Consequently, because of this new insight and ability that we have these longer sets of data and this new type of analytics can be performed, a lot of data streaming platforms are also used as event-based databases in addition to their traditional data integration duties. So now that we have some historical context, let's look at two very different approaches to stream storage inside data streaming platforms. The first is partition-based storage, and the second is segment-based storage. As we discussed previously, LinkedIn was facing a scalability issue, not only in providing end-by-end data integrations, but also in the sheer volume of data that they were trying to process. By adding a single unified log structure, they were able to eliminate the need to have n integrations per data source, but the trade-off was longer data retention. They were publishing a lot of data into a single log structure that was being consumed very slowly or at different rates, therefore it had to be kept for longer periods of time. This need to support multiple consumers resulted in a need to retain the data for longer periods of time, and as a result necessitated that the log storage solution was horizontally scalable from a storage perspective, right? You need to be able to store, if we're going to store data for days or weeks or months, we cannot possibly store that on a single physical machine, no matter how many disk drives you stuff in there. At some point, you have to have an approach that's horizontally scalable, one that can leverage the storage capacity across multiple machines very easily to make sure that you don't lose any data. This is critical data. It is your pipeline coming into your system. It is your event-based database. So it has to be reliable. It has to be redundant. It has to be horizontally scalable. Now, the approach taken by the developers of Kafka is called partition-based because it takes the single unified log data structure that's used for storing data on an individual topic and physically divides it up into a predefined number of smaller logs known as partitions. Right? Now, once this number of partitions is set, that's it. It's really hard to change this number, as we'll see later on how this becomes a bit of a challenge when you're trying to scale up besides the number of partitions. But the advantage of this is that each of these partitions can then be assigned to a single physical machine for storage. Thus, a single Kafka topic, AE, as stored in a unified distributed log structure, can with n partitions leverage the storage of n physical machines. So now you have your horizontally scalable storage. This slide here shows one possible distribution of records across these partitions and represents the ideal state. So in a perfect world, the data is evenly distributed across the partitions in a round robin fashion. So
The conceptual log shown here at the top logically has entries 0 through 21, and you can see that they are evenly distributed across the partition. So entry number 0 went to partition 0, entry 1 then went to 1, 2 went to partition 2, 3 went back to 0, so on and so forth. So this really round robin distribution of the data, 1, 2, 3, 1, 2, 3. Make sure that the data is the ideal scenario, the data is distributed evenly. This is not always the case, but for most purposes in analytics, we consider this to be the base distribution of the data, right? So this approach has pros and cons. Again, the record comes in, it's hashed, and then this hash is going to go across the number of partitions and it gets redistributed there. Now this approach can be modified. You can do hashing based on key records. So if you want to do hash based on a key and you have a skew in your number of keys, for example, large number of keys, values of one particular value, not others, then that could skew the distribution of the data across the partitions. But the trade-off is that the data with the same key is kept there together, which has efficiencies when it comes to querying the data for the event-based database, and some better performance, as we'll see later on, since we're focused on latency. Having to scan a single partition rather than all of them will have that approach as well. So now that we've talked about the logical structure of the partition-based storage, let's talk about the physical deployment, right? Where they actually get placed. So with Kafka, each partition is stored in its entirety on a single broker, right? A partition by itself has to coexist and can only exist within one single broker. There are replicas. They are always replicated for high availability. So each partition has a corresponding backup copy on one or more brokers. But the leader and the base one where all the data goes first is kept in a single broker. Therefore, each broker, the physical storage capacity of that individual broker is in effect a hard limit on the size of that individual partition and how big it can actually get. But that is the simplified version of that, right? In reality, your Kafka cluster is going to have more than one topic. And therefore, each broker is often going to have to store multiple partitions, each different ones for each different topic. So which is I represent here with different colors, right? So you could have partition 2 of the purple topic, and you have partition 1 of the blue, and partition 0 of the green, and so on and so forth. The reality being that each of these partitions that the broker is assigned for storing are competing amongst themselves for the disk storage capacity on that broker itself. This makes the disk itself a shared resource and impacting the total storage capacity of the partitions themselves. Also getting some I/O and networking traffic across the topics as well. So if you have one topic, if this broker is serving a topic that's very busy, those resources might be consumed and overwhelmed, and it's unable to serve the other partitions that it is responsible for with the same level of resources, because one or two of them are consuming and taking over all of the resources on that individual broker. A further thing to note is that once any of the partitions of a topic become full, more partitions must be added to the topic. So when you first create when you create a Kafka topic, you have to ahead of time specify how many partitions it will have, and those get laid out and assigned. If you guess wrong and one of your partitions fills up, now you're in for quite a treat, because now you have to add more partitions. This is called re-partitioning, which in effect you basically say, I was wrong, I don't need 3 partitions, I need 4 or I need 5. This triggers what's known as a rebalancing event, in which all the existing data in the topic must be read and then redistributed across all the partitions in the topic. The goal of this process is to end up with n+1 or n+2 partitions that all have some storage space, right? So you cannot just have one new empty partition appended on the end and full partitions based on the fact that the data is distributed round robin, right? So you're not going to have all that data go there. That's why you have this whole rebalancing event, during which time the entire topic is offline. It cannot be queried or read, and it cannot be written to. And this is a huge impact on latency when you're querying the topic, when you're attempting to query the topic and do performance, any sort of measurements during a rebalance. We don't do that here during our performance evaluation, but it is something to be aware of, that these micro outages
can impact the performance of your partition-based system. So in summary, the storage model, partition-based model, is it's simple and fast. All the reads and writes are sequential. They're done on the same device, so you avoid network hops. A single broker must have enough space to cope with that replica. So very large replicas force you to have very large disks. That's kind of a con. And scaling out your storage, as I mentioned before, by adding partition requires a rebalance, which is a big impact on your availability, your system availability, and data availability on that individual topic itself. So that is definitely a con when it comes to that storage method. Now, a segment-based storage scheme takes the single unified log data structure and physically divvies it up into a sequence of segments. So you can think of these segments as an unbounded list of that can grow to infinite size. Rather than having a pre-carved out set number of partitions or buckets to put your data in, we're going to basically create a growing list of these segments and use that as a metadata layer to keep track of where these individual segments are stored. These segments are then evenly distributed across nodes inside a separate storage layer. And unlike the partitions in Kafka that are stored on a specific broker in the cluster, these segments can be placed anywhere that has storage capacity. So within each segment, approximately 50,000 records are stored, but that is also configurable, so you can make these segments as large or small as you want, and it's continuously rolling over and changing this information. So let's look at how this data is distributed when you're publishing to a segment. So unlike the partition one, where it was distributed up front across 1, 2, and 3, you can see that the data is always published to the most current segment. So the first 50,000 messages here were put into segment 0. It's closed. It's done. Nobody else is writing to this. It can now be read offline on a separate I/O path, but it's no longer open. The next 50,000 records were added to segment 0, and now that segment 2 is open, we're writing this next record here. We're just appending it. So one at a time. That's it. All previous segments are sealed and cannot be written again. There's some metadata associated with that, MD5 checksums, etc., to make sure that the data is not corrupted. And then these segments can be replicated across the nodes, but they're much smaller sequence, and again, they're appended. So segment 1, segment 0, 1, 2, 3, 4, 5, they just keep going. There's no rebalancing required. They're just distributed across the nodes. So each segment is stored in its entirety in a single bookie. This is the separate nodes that make up that distributed storage layer, and they're independent of one another, right? So this is your this is your view of the logical topic here. This individual blue line represents your logical view of a unified log, and these red entries indicate what your segments are. They're very small pieces of metadata that say, hey, for my particular topic, I have segment 4. These are the red ones, so this would be segment 1 and segment 2 and segment 3, for example. This is where they sit. That's it. And then you have a pointer to where they are. When you create a new one, you add a new entry here to this metadata store, and then you find a new bookie on which to write the segment, and you just add it. You start writing the data. Once the bookies become full, you can just add a new bookie in, and that can immediately start taking over that write. There's no rebalancing required, right? So the metadata store just maintains all of this. So when you need to grow your cluster, you just add more bookies, and that data gets added very easily. So this information, it goes down a little bit. We'll talk a little bit about the I/O isolation here, because it will have a big impact on the performance later on. This is the internal read and write path inside Apache Bookkeeper, which is the foundation for segment-based storage. Now it uses a write-ahead log mechanism for durability. So when the data comes in, it is first written to this journal in sequential order in an append-only manner before being persisted to the main ledger disk. This should remind you exactly of the commit log in the database. It performs exactly the same. It's an append-only data structure, very quick, single consumer. The bookkeeper then separates the storage device used from the journal, which is your write-ahead log, from the main ledger storage, and the journal is usually stored on faster, more durable disks, either SSDs or NVMEs, to handle this write-intensive workload very efficiently. And tabling reads, when people are coming in and try to read the data,
information back and I'm querying the information, you try to read it from this memory table. There's an internal cache of where the entries are, and only catch-up reads will be served from the ledger disk and index disk. We have an index disk as well that keeps track of where the entry is in the longer-term disks. As a result, the heavy reads in Bookkeeper will not impact incoming write performance because they are served by different physical disks. We've isolated the I/O across multiple devices so you get full throughput of both, and they don't compete for one another. It not becomes a physical bottleneck like you have in a partition-based storage where you're trying to write to the same disk that you're reading from to serve reads. Regardless of how big your device is, it's a single I/O channel. You're going through that disk, and that's going to be your bottleneck. This is not the case with segment-based storage. Now, segment-based stream storage, the pros and cons are, again, the data from a given topic is spread across multiple machines, and you don't have to predetermine how many machines you're going to need ahead of time. This distributes the reads and writes across multiple disks, as I mentioned and showed in the previous slide. There's one disk for writes, for inbound writes to append-only log, and there's a separate disk used to serve catch-up reads or read historical data. Each bookie only needs to serve a subset of these requests, which can increase the total throughput and latency. So again, if you're doing a query and you're reading data across multiple windows, chances are, because these segments are smaller, 50,000 messages per segment, that you have a higher probability of being able to read from multiple bookies simultaneously, getting the full parallelism effect of those reads and writes in terms of throughput and latency. And last but not least, when you need to grow your storage capacity, your storage of your cluster, you can simply add more bookies and they'll start getting written to right away. This is because of the nature of segment-based storage. Every time a segment is closed, a new segment is open, and then you arbitrarily pick a bookie from the pool of bookies. A new one that's added is just as valid as one that's been around forever, as long as it has space. It can be selected for writing and immediately start data being written to it. There is no rebalance, no repartitioning of the data needs to be done. So these are all advantages to that approach. So again, just to summarize those, this graph shows them here. In Apache Kafka, this is your logical view. You have a large single partition. It is east. You have a leader. The same data is also in the two replicas, and it's stored on multiple bookies. All log segments are replicated across the brokers, and all the data comes in here. It's one logical structure. You can't increase the size. Now, the same particular topic in Apache Bookkeeper and segment-based mechanism is broken up instead like this. So there's multiple segments, smaller segments broken up and written across more bookies here. So again, these segments are distributed by 3 replicas across different bookies, but if you need to do a query that hits segment 1 and 2 and 3 simultaneously, bookie 1 and bookie 2 and bookie 3 can all serve these queries in parallel. This is why we get the advantage when it comes to performance, and we'll talk about that here in a bit. So now that we've reviewed the architectural differences between the two storage methods, let's review the performance of both with a focus on latency. Using the Open Messaging Benchmark tool, we benchmarked the performance of both Kafka and its partition-based storage and Apache Pulsar and its segment-based storage. Using the Open Messaging Benchmark ensured that we were running an identical workload against the platforms that were deployed on identical infrastructure. As we can see here, this is the actual load itself: 1 topic, 1 partition, 4 producers, 1 consumers. And you can scan this query code to download a full copy of this report. This is showing you the write throughput capability of Pulsar being 2.5 times better. As you can see from these results, the segment-based storage of Apache Pulsar provided consistently better latency across all distributions, particularly at the P99 level and above, where it really starts to break away and show significant jumps across the two. We're at the end, we're achieving consistently single-digit published latency, and this is 100 times better than Kafka under the same data durability guarantees, i.e. without journaling enabled. This is to make a fair comparison. We don't write to disk before the ACK
Same with Kafka. These are the differences. These are the numbers to compare. Similarly, segment-based storage also provides significantly better historical read performance, which is important when performing streaming analytics on older data. I know this is focused on latency, but I wanted to show you that this is not a trade-off. You're not trading throughput for latency. You actually get better performance on both. It goes back to the parallelism across that, which we'll review here. So again, much better performance all around, higher throughput, much higher latency. Let's talk a little bit about why the results are the way we are and why they ended up being the way that they are. So one prominent factor contributing to Kafka's relatively slower performance lies in its overall design. While Kafka was designed to minimize network jumps by having information stored on the same disks, it does not inherently provide good I/O isolation, leading to substantial interference between read and write traffic. Right. So again, as we showed before, each broker is serving multiple partitions simultaneously. They each have to share those resources of the physical machines, whether it's network or disks, and so they all compete for that, and it becomes on higher loads because a really significant impact. This lack of isolation between the disks and the networking and the CPU because it acts as both the serving layer and the storage layer, becomes a bit of a bottleneck in the overall performance once you start scaling it out. Instead, Pulsar's architecture has been designed with a focus on achieving strong I/O isolation, which is one of its key architectural strengths and highlighted by its segment-based storage distribution. Now, despite potential network bottlenecks in its architecture, Pulsar outperforms Kafka in terms of speed in a lot of scenarios, as we just saw. This advantage stems from efficient I/O isolation, optimized read and write performance, expandable network bandwidth, and more scalable connection handling. Everything coming down to you can throw more resources at it, do it in higher parallelism, get much more lower latency, everything that you want in a system, and the results and the performance tests speak for themselves. I'd like to thank you for attending my talk, and let's please stay in touch.